Cool.
Hello, and welcome to the latest edition of the New Stack Makers podcast. This week, recording live and live streaming from the show floor of KubeCon and CloudNativeCon in Barcelona. And today's topic, we're going to delve into the fascinating overlap between HPC, high-performance computing, and Kubernetes. Both are forms of distributed computing, and we're very interested in what one can learn from the other and how we could perhaps use Kubernetes to do some of those HPC jobs. And our panelists today, we have to start with Alfonso Santiago, and he's a researcher for Elm Biotech, which is a spin-off of the Barcelona Computing Center.
Yeah, exactly. So we started with the spin-off like 6 months ago, and it's trying to take to the market a tool that we have been developed in the Barcelona Supercomputing Center for the last 15 years.
Excellent, excellent. We'll dive right into that in a second. We also have Charlie Daniels, who's Charlie Davies.
Davies, yeah.
He's a co-founder of iGeolise.
Or iGeolise, depending which side of the pond. But it's not the best name. We know that.
But you have a very fascinating
technology. We have essentially built a way to search maps, data, and the world around us by time instead of distance. You can say, what could I do within half an hour by public transport, driving, walking, or cycling, or all those combined? We now do that in 35 plus countries, and because of that, we have a big data issue, of which HPC and Kubernetes and then has been very helpful.
Nice. And also we have TJ Fontaine, who is a software engineering consulting member of the Oracle technical staff.
That's right. I've been working here at Oracle for just over 4 years, working on building what we now call OCI, Oracle Cloud Infrastructure, where I function as an architect across our container-related portfolio, so our managed Kubernetes, our functions as a service, our container registry, et cetera.
Nice. All right. Fantastic. And the HPC space, when Kubernetes came around, I thought, oh, well, this is high-performance computing. It's the same thing. It's distributed computing to execute a larger job. But actually, the kind of worlds are different. But that's no reason that one can't learn from the other. So I'm very curious about. Both of you are HPC veterans, and you're using Oracle Cloud, or you're using a cloud service of some sort. And so what's the transition like? What's the benefits? What's going on? First, let's start with Alfonso. Talk about what you guys are doing and where the idea came from. And
Perfect. So as I told you, the spin-off has been created more or less 6 months ago. And it's actually a spin-off of the Barcelona Supercomputing Center. On the Barcelona Supercomputing Center, we have been building this model of the human heart.
All right.
So it's a beating human heart inside of the computer. The good thing about this model is that you can try and test different techniques and apparatus inside of the on this organ, right? So this is a great tool, a super powerful tool to be used by clinicians and by designers of biomedical devices. There are two main problems with this. These computational simulations are really hard to configure, right? Because you have like thousands of parameters that you have to know and to the detail to make it work, right? And the second problem that we have is the computational cost of these simulations. Because even though it's very efficient, they are computationally expensive. So we need more or less about 200 to 500 cores for each simulations and about 2 hours, right?
And that's a single program. That's a single
execution. So the thing is that with this type of resources, I mean, not everyone has this type of resources on their offices, right? So what we're trying to do is trying to tackle this problem with Oracle Cloud, trying to democratize this tool and make it available for people that didn't have these type of tools before, right? So we have a front-end web application where you can configure the executions, that they are very clinician-friendly without all the numerical complex parameters, just the physical parameters that you want. And then we have a backend where we schedule the different executions and run the different executions on Oracle Cloud.
And did that involve, was this software designed originally for HPC? And was there a lot of work to move it to a cloud infrastructure?
So this software it was originally developed to run efficiently on supercomputers. It is actually an academic code, right? So when you're trying to move it to more industrial framework, you have to tackle some issues. So for example, this code generally runs on supercomputers, on computers that are for research, and these type of computers have very optimized compilers and libraries for this type of software. So we need, if we want to keep the efficiency on the cloud, we need to port this type of optimizations to the cloud, and we need to make it run efficiently also into the cloud to have the same times in one side and the other. So these are mainly the two big challenges that we have on the topic of.
And so, do you use Kubernetes to orchestrate?
Today we are using virtual machines to run the case. So we are using Slurm there is another queue manager to execute the cases. But in the future, what we are trying to do is creating this virtual population of hearts, so you can try different devices on different hearts. And for that, we are planning to use containerization solutions that are being developed right now. And in that moment, we probably are going to use Kubernetes to manage those applications, because if you need to run 10,000s of different virtual patients to test the population, you need an efficient and smart workload manager.
And so Slurm was an orchestration workload manager for academic and specifically in biomedical use cases where it's been mostly used, right?
It's like it's a workload manager generally used for supercomputers. It's like it's not specifically for biomedical applications, but for scientific applications.
And it also has some benefits around the topology, like for instance using RDMA or things like that, right? Like you can if you have a workload that's for supercomputers, you usually have a very fast interconnect among all of the worker nodes.
So, and also it's true that this type of workload managers can be simpler, because generally supercomputers, you have like more homogeneous clusters, and you have everything on site. So you don't need a smart tool to distribute this type of jobs along an heterogeneous cluster. So you can use this homogeneous cluster. It's much simpler to run these type of executions in a supercomputer compared with cloud environments.
One thorny thing I remember from some of the HPC programs is that if one node goes down, the whole job has to go back to the last checkpoint, I guess.
Exactly.
And how do you? Is this something Kubernetes could help with, actually, theoretically?
Well, the idea is that it does, because once you have your execution on a container, it is independent from the others. So if that node, for some reason, fails, you still get the other hundreds or thousands of executions.
Excellent. And Charlie, you're doing some pretty heavy lifting when it comes to computation and data.
Nothing as fascinating as reproducing the human heart. Really hard act to follow that one. So we essentially ingest a huge amount of transport data, whether that's the driving data, walking data, cycling, and most importantly, the public transport data that we take in.
Nice.
And you would consider public transport data to be fairly static and the same, but it changes actually much more regularly than you'd believe, whether there's services that are running one day as engineering works, and when you multiply that not just by the city but to the country level, and then in the 35 countries that we're in, and the size of our organisation, there's about 30 people, is a really hard challenge, especially when you're then trying to actually have a product that people can use on a day-to-day basis in real time. So, we took our journey in terms of high-performance compute. Really, it was more of how do we get a product that we can sell. So it was, really on a shoestring startup. How do we take this data? How do we refresh it in such a way that we can put it back onto our runtime servers and have everything available? And the code that we were running was really quite bad, in the sense that it had grown from the sense of, we've got this country, let's add this country. We've got this data format, let's add this data format. And it just got big. That sort of Leviathan process that comes out of those ideas that when you start, then you get someone paying for it, and then you've got clients relying on it, and suddenly you don't know which way you should go, you know, your technical debt versus your potential revenue and like all your near-term revenue.
Huh.
So when we started speaking to Oracle and then introduction to Kubernetes, we were actually starting using the bare metal instances, which are these really, really high performance instances that we were using to take, for example, all of the public transport data in Germany or Israel or Spain or the whole of the United States, for example, and making sure that the data coming in is correct. Because most of this data has been put in by a human being at some point, and human beings are terribly unreliable, including myself. And afterwards, then making sure that it all makes sense. But as we replenish that data, that it also makes sense in a historical term. So you can't now get from this side of the country to that side in 90% quicker than the day before, for example. And this problem just got more complex and more complex and more complex, and we kept on adding in other layers and other countries to the point where, you know, to process our data was taking longer than it was taking for the data to be valid.
Right.
So the data was being replenished faster than we could replenish our data sets. Now that was even more complicated when more and more users started using it through our clients, because people get very attached to travel times. You know, if you tell someone that it's going to take 35 minutes, they may turn around and go, I can do it in 33. So we always need to be very transparent and very clear around the data sets we're using, how we gather those data sets, and how we process them. And what Kubernetes enabled us to do was to basically take not just the countries, but down to the cities and even the modes of transport and those data sets and test them. So we can push them out. We can basically just take one country or one different data set, whether that's in our data team, so the data research team, who don't have to be that proficient in coding or our entire stack, but they can launch, they can test, they can put that back, and then that can go into the city data, country data, and so on and so forth, until we have what we believe to be, you know, the best data set we can get to deliver the product to our clients. And that actually took us down to we can now do that for those 35 countries in about 8 hours. So we can just do that several times a day now, instead of waiting for over 2 weeks.
And so that actually enables the business, the business model.
Exactly. So for us, you know, we're again not as sexy as the human heart, if the human heart is sexy. But in terms of actually, you know, for us, we didn't take in that much investment at all as a company. So we've always been quite scrappy in how we've gone and got clients and how we've maintained them. And for us, it was just a state of the desperation of trying to serve those customers and those near-term revenue versus the technical debt that we had built up. And not just technical debt in code, but just the process of how we're doing stuff. And one of the other things we're having is that we were able to just run servers all the time. And part of the thing we're trying to do as a company is to get more people to use public transport and to limit, with some of our new products, to limit the amount of vehicles that are needed in an urban area to reduce pollution levels. And it sort of seemed a little bit contradictory that we were then just powering up all these servers. You know, these are very hungry machines, and we've actually then reduced our carbon footprint or our environmental footprint as a result as well. And we're trying to get some analytics out of that as well to show that the whole of what we're doing is really geared towards helping people reduce their emissions, but also that we're doing that as well. And that's sometimes a thing that gets missed. And I'm not a massive, you know, I'm not here, you know, always talking about the environment, but you know, we've seen recently, and especially in the UK, big amounts of protests around this, but there's lots and lots of servers out there running lots and lots of stuff, probably very inefficiently, and Kubernetes has helped us become a lot more efficient.
Nice. It's a fascinating technology to it. You were demonstrating this before, but
yeah, it's app.traveltime.me. If you want to have a go, my marketing team will now.
There you go.
Now say I've done my job.
But it can tell you you can go this far in 30 minutes or 40 minutes, rather than giving you like 5 miles. It can actually tell you, all right, you go down, catch the bus. Here's how far you can go.
Yeah. So the perfect use case for here is always, you know, I need to be not just in Barcelona, but at this conference center. And in conferences, you know, the majority of hotels get booked up very, very quickly, and then everyone raises their pricing. But you could stay in a hotel within 45 minutes from here that could be way cheaper.
Oh, yeah, get
but
one.
But you could actually get here quicker than some of the other hotels. And it's removing that guesswork from those location-based searches. So it's not seeing everything on a map and then copying and pasting that address into another application and finding the route.
Nice.
It's having all of that stuff up front, so that if you're trying to monetize locations online, whether that's property, recruitment, hotels, anything like that, we can remove the guesswork and make sure that there's much more relevancy driven in the searches themselves.
It's also, I would imagine, very handy if you have to get to a birthday party and don't have a gift yet.
If I arrive late for a meeting, it doesn't look good.
Wow.
Yeah, that's why I set all of my watches and clocks about 2 hours early. Yeah, it seems to work.
Excellent. Well, TJ, I'm hearing a lot of democratization of what was formerly, I guess you would call HPC workloads. And I know with like the U.S. Laboratories, you have to, if you have a big job, you want to study the human heart, you have to put in a request to go to Lawrence Livermore, and maybe you'll get the hours. This sounds like this is kind of opening up a lot of potential work.
I mean, right. Like, basically, what's been locked up for a lot of people using supercomputers is the idea of, like, I have an API and I can go run my job whenever I want to at the time that I need to do it. Or I can, and that infrastructure doesn't always have to be, sitting around waiting for my job to run, right? Like, both of these scenarios are being talked about, and that's really what the whole cloud premise is supposed to be there. You get a billing model that you only have to pay for what you want. You get you get greener experience for that, because then everybody can start spinning down those things. And from a supercomputer side, you're not waiting in line for everybody else to complete their job when it's time for you to go run yours. You can just do it on demand when you're ready to run that workload.
Yeah, and also you don't need to have physically the supercomputer in your office.
That's right.
You can. I mean, that's expensive and takes a lot of place and energy. I mean, you can run. What we're doing here is like trying to put the supercomputing power to the people's hand, to the clinicians' fingertips, right? So this is the critical thing that the cloud is supporting.
Yeah,
it's really just making everything as lean as possible.
Absolutely.
In every single way, the delivery, with the physical location of it, the energy driving it, and the availability of it as well. We have guys that use our data in a sort of GIS sense, so this sort of business analytical sense, and they were running, some of them, very heavy-duty machines. They were expensive machines. They're just sitting there. They may get a question that requires those answers maybe once a week, but that system's always there. We can now deliver that over an API straight into their application, and they've only used it for that snap that they need it, and that's it.
Yeah, and so like all of this is really important, and it's if you think it's not as sexy to model the human heart, talking about building infrastructure is really not that sexy. But we didn't get into it. I mean, it's nice to know that people are using it for either for improving my commute time or for saving my life. But we didn't build it. We didn't build the cloud specifically with those ideas in mind. But we knew that what we wanted to do was actually really go out there and solve for any kind of use case. Our particular use case that we thought about in the beginning was like the database. Like, what can we do to, obviously we're Oracle, we have a really big business around database, so we built things that made it really good for us to do that. It turns out that it works out really well for the rest of HPC workloads. So you can run bare metal instances. We also do, RDMA, so that you can actually have massive data sets and then address them across all of that with low latency, right? Like 100 gig between that. There's no other cloud that you can do that on today, and it's not because those other clouds don't see the value in it. It's just that we build it because we have these databases, and and data is usually at the heart of a lot of these workloads. And so, really we were optimizing around that, and it's been really fun to work on, solving these really complex use cases and then being able to attach it to modern state-of-the-art technologies. When you were using your supercomputer, you weren't really thinking about how could I ever use containers necessarily to use that. That wasn't, you had your tool chain, you had all of that life cycle, and that's what you were going to use. But now that you're in the cloud, leveraging those things, you get to think about, how would I solve this problem today with microservices? Or, you've got a front end, you've got a back end that's doing this. You can split up the concerns, and you can use whatever tools that you want to solve those problems, be it, whatever orchestration management that you have, or Kubernetes, containers, or VMs, or bare metals, if that's where your workloads can run. So our job, is to really get out of the customer's way and give you as many of the building blocks that we can to solve those problems.
Yeah, and the quality of the services that have come out, especially the speed and the performance and the low latency and the other stuff around that has been really helpful for us. But it's also, you guys do a great job because you are selling an infinite proposal in a finite world.
Right.
It is unlimited computing power whenever you need it. but we need to make sure we have those computers. It's not as if we can just click fingers and suddenly they just multiply.
Yeah, no.
There is actual physical infrastructure out there that has to be there. But things like Kubernetes can make sure that is being used much more efficiently.
That's right. Yeah,
that's where it really, really is helpful.
It allows you to. Well, we use it ourselves to increase our own density, which allows us to reduce our base footprint, and then we hopefully give you the ability to leverage it for your own purposes, so that you can drive up density and use smaller instances if necessary, or et cetera. And then the really thing is having as much of a big pipe as possible to get the data into the region, right? Like your data is really, your lifeblood,
really important.
And that's the expense. I mean, in many ways, getting the data there and then computing on it is secondary. How do I get the data there, and how do I know that it's always going to be available for me to run my simulations on or my analytics?
Nice. So what is the preferred configuration for HPC-style jobs? I'm hearing bare metal quite a bit. And so, I mean, I guess you're bringing your own distro, containerization, of course. But, I mean, are you offering GPUs? Or are they...
Sorry, real quick, as a cloud provider, I will say we have a variety of shapes that you can leverage from small virtual machines to virtual machines with GPUs to bare metals with GPUs to even our HPC shapes, which have RDMA 100 gig interconnect, right? So like you can pick any of those that you want. After that, I'd leave it to you.
Yeah, I mean, for us, it's understanding what is available. And then the balance, of how quickly do we want to do something versus the cost of that. Mm-hmm. Things like the availability of those instances. Can we get a cheaper instance at a certain time? Can we run the process then? Do we need it done in 8 hours, 15 minutes? Is 8 hours, 10 makes it? For us, it's not necessarily about the runtime environment, about accessing it straight away, but those batch processes that we can really shrink down and then make everything else more efficient on top. So it's a different question we're trying to ask. I mean, there's lots of things that we could take advantage of GPUs, but at the moment we dedicate everything on just the standard CPU, and then very high levels of memory as well. And we do go right down to the bare metal, which that's what the service is called, bare metal. But then also virtual machines on top of that, and we don't do any of the serverless containers at the moment, but just at the moment distribute them all by Docker, etc.
Yeah, in our cases, something similar. We choose the solution strategy depending on the type of problem that we're trying to solve. Mm-hmm. This is some sort of hierarchical pyramid scheme of simulations. Mm-hmm. So the idea is that you can run a lot of very simple, cheap simulations. Mm-hmm. So for that, containerization solutions is the best. And on the other extreme of the range is when you have very expensive, detailed simulations that has a lot of physics inside and that they are very complex from the physical and computational standpoint. So in those cases, we want to run bare metal because we want to run as optimized and close to the hardware as possible, right? Yeah. So we also target, it depends for each case what you have to use to get the most of it.
Where do you guys store your data? Do you use like NVMe or do you use object storage or?
We use a combination of both. We use NVMe for the runtime environments, like pulling out more of the detailed data. So not just like the top level. What we do is about returning a time value, but then we do fare cost, then we do route description, and route description is going to have stuff like the agency name, and for that we have to have NVMe storage to fast deliver. Then the object storage is great for the historical stuff. So we might be used on. We get used on so many different things. So like trying to find a property, trying to find a job. We get used in the UK to distinguish, to make sure that betting shops aren't within a certain amount of time of each other, because there's a competition commission around that. Yeah. Now, that's not something I ever dreamed that we would ever be used for, but that gets used, and in some cases that's a commercial, well, it is a very commercial, responsible set of data, and if there's a problem with it, we need to go back and save that data. But when data's when the public transport data driving is changing all the time, not only do we need to keep current, but we also need to hold all that data behind us as well, and that's what the object store's very valuable to us, because we can just retrieve it almost without thinking. It's just there. Yeah.
So in our case, it's mainly NVMe because the configuration of the case is really simple, actually. We actually have a problem that we are solving now, that is with the results, because sometimes we have like gigabytes of results, right? And you need to develop that to the web client that may be on the other side of the world, right? So we are trying to optimize the results that we get, so we can only provide and transmit to the other side of the world just the slices that the clinician requires, right?
Interesting.
Do you guys do a lot of shared memory among servers? I remember that was a thing with HPC.
Yeah.
Grouping together as much RAM basically as possible.
Yeah. Again, it depends on the case. Yeah. But we generally need to run more than one node at a time, because these are generally large cases. Again, if it is a small case where those type of cases that you run maybe 10 or 20 on a node, you just use one process. But for the larger cases, more complex with more physics cases, we do run MPA, and we need to use distributed memory to solve those cases.
Yeah, I mean, so on the database side of things, obviously, and the Oracle cluster side, like one of the reasons why we have, like, you have these massive data warehousing kinds of things, and there's these compute jobs that need to run across that, and so that's one of the main reasons why we included RDMA in the cloud, is to be able to do massive memory allocations, but also these bare metal instances already have a ton of memory in them.
Yeah.
So like, north of half a terabyte of memory, right?
Not so much
depending on the instance type. And so it's if your data set can fit is less than 500 gigs or whatever, you can be okay.
And there's always those things, memory now is a bit, cheaper. I was actually discussing with someone earlier on about ages ago. There was a flood. I think it was in Thailand where they produced all the memory. Memory prices shot up. It was about 10 or 15 years ago.
Really?
People were going around stealing computers just to steal the RAM, because it was just so. And then now you can get a half a terabyte instance like that, and it's so different. But for us, again, it's another balance of, do we make code more efficient and the data structures more efficient, so when we process stuff that we need less memory, or can we move faster and do more? We know the code could be better. I mean, code can always be better.
It could be more. It could be optimized.
It could be optimized all the time.
But who wants to do that, right?
Yeah. Do we need to do that? And there are things where we would like to do the shared memory across multiple instances, especially if we were to do sort of multi-country lookup. So, if I'm at Heathrow Airport in London or Barcelona Airport, where could I be within 12 hours across the globe? That would be very interesting. But use cases right now in terms of where we're looking in clients is more sort of city or country-based, and the surrounding countries, not air travel or the globe yet.
Nice. Now, something I'm very curious about is the effect that the cloud will have on the traditional HPC community. And, these are a lot of government universities and other academic labs. They're buying hundreds and thousands of servers, and they're trying to get it just to boot up, basically. And meanwhile, there's big competition between the U.S. and China, who can have the biggest computer, Are there jobs that are inherently supercomputer-based that could never go on the cloud, or is it pretty much just go to the cloud?
We certainly have not found that limitation, but I guess that's more one for maybe an academic.
So I think that the answer comes from other side. National laboratories for supercomputing are a way of funding supercomputer resources for public research, right? Right. So, and the cloud has other targets, has industry and private business, right? So I think that national supercomputing centers will actually never fade away, because you still will be doing HPC research for the public sector, but the cloud services will start to grow, because the truth is that a part of the problem with HPC applications to the industry is that it's hard for an industry to access HPC resources on national laboratories. Right? So that's what allows the cloud. Allows to have that type of supercomputing power to the industry. So I think that the national laboratories will never go away, but we are going to start seeing more and more every time have these cloud services and cloud applications, and as I said before, supercomputing powers at the fingertips of the clinicians and everyone. Right?
Nice. Do you think it's possible that people would, when you're building, not coming from a background of building these kinds of ecosystems, would you prototype the workloads and the jobs in the cloud, and then when you have time, when you can go actually run them on the supercomputer, you would know that it's going to work? Never having had to debug.
Yeah, the truth is that the cloud environment gives you a lot of tools that makes the platform much more flexible than a supercomputer, right? Because you're very restricted on what you can do. So that's something that I haven't thought, but it's a very good idea. Once the tool on the cloud is pretty well developed, you can run 1,000 of simulations on container solutions, and then when you want to run the largest case, then you need to use 100,000 cores or whatever. You can move to the supercomputer. That's a solution that I see.
But do you think as well, from the question of whether governmental authorities will have their own, is still going to be down to the security factor of not putting it on the cloud as well? Do they still get hung up on that? The fact that is this sort of ownership? We did this, we ran it here. Right. It was inside this university, this region, this government authority. And then also the security layer on top of that. Yeah,
well, that depends a lot, I think, on the regulations of each institution, right? Yeah. So in our case, our spin-off has the exploitation regulations for the code that we develop, right? So we can do this. We can run on the cloud and then run on the supercomputer as we wish. But I suppose that it depends a lot on each research center how the policies are there, right?
Yeah. Okay.
I'm just imagining there's some work in like intelligence or defense. It's just never going to be.
Yeah.
But those are the few jobs.
A problem that we will face in the future in some point is what we do with patient data.
Yeah.
Because that's very sensible, right? You cannot take the images of a patient from a hospital and put it back on the on your own cloud. I mean, nowadays each health institution, like mid or large health institution, has its own cluster where they store the patient data. And generally, spin-off that works with medical data, what they do is running their machine learning algorithms, let's say, on the cluster of the hospital, and then taking the trained networks outside, right?
Right.
But that's something
they train on the supercomputer or in the cloud, and then use the model locally for classification.
Nice.
Yeah. So that's a problem that we will have to tackle at some point. I mean,
so what you're saying is there's a world of edge model verification for clusters that we haven't figured out. Edge HPC.
Wow. Yeah.
I guess startup idea.
I don't know if the HPC folks would like being considered edge, but well, in many ways they are being out there, the cutting edge. Anyway, this awesome talk. Any closing thoughts? Any closing ideas about HPC and Kubernetes and the cloud? Something we haven't discussed yet.
I mean, I think there's a lot that the workloads and the practitioners that are going out there either leveraging Kubernetes today or using other orchestration environments that were previously used on supercomputers. There's a lot that can be learned in the Kubernetes ecosystem, and there's a lot that Kubernetes can do to improve that and make it so that the reliability that you look for, being able to scope jobs down, if you need shared memory, being able to describe your resources for those things in a declarative way is still really compelling. I mean, Kubernetes is exists for a reason because it's a lot easier to describe your workloads for those things, but it's not meant to fill every gap yet. And so there's a lot that it could do. So as you guys start to identify those things, it's really important that you make sure anything that you see as a gap missing from those things that you let people know so that it can take advantage. So I think that there's a lot that it could solve for you today, and I think that there's a lot that it can also learn and improve to be even better for you guys.
Yeah, I mean, just closing from us is, we've only really just started on the journey of using it, and that just came down to the fact that we had this big problem about processing loads of data, and this was a solution. From that, we now run our web applications on Kubernetes because it was just the next natural thing to do. But there's lots of stuff in the runtime we could do. If someone does a search in Japan and we need to deliver the data right there for that instance at that, that's exactly what we can use it for. And yeah, we've got a lot more to do. In fact, too much. But anyway,
it's always the case.
Yeah, of course. I mean, you need to use each solution for each problem. I mean, for each problem that you have, there is a best fit solution for that problem, right? The truth is that Kubernetes has been in the market for not so many years as compared with scientific computing. Right?
Yeah.
So this is a framework that Yes, sorry. The supercomputing Kubernetes and the supercomputing resources for public research, it was what have been used and developed for the last maybe 50 years, right? So, but now this new tool appeared, and it's much more flexible, and you don't need to have your computer under your desktop. So, so it has a lot of future, and I don't think that it's gonna replace every other tool that is actually now, but it's gonna give you it's gonna give us a new flexible tool to attack some of the problems that we couldn't attack or weren't efficient enough with the tools we had right now.
Nice. All right. Well, thank you, gentlemen.
Yeah, thanks so much for having us on. Really appreciate it. Thank you.
Yeah,
And thank the audience for tuning in, and we'll see you soon.
All right. Bye-bye. Bye.
Bye.